Next, I take the opportunity to introduce you all to the next speaker for today, Professor R B Pachori. Professor R B Pachori received the BE degree with honors in Electronics and Communication Engineering from Rajiv Gandhi Technological University, Bhopal, India in 2001. The MTech and PhD degrees in Electrical Engineering from Indian Institute of Technology, Kanpur, India in 2003 and 2008 respectively. He worked as a postdoctoral fellow at Charles Dillinois Institute, University of Technology of Troyes, France during 2007-2008. He served as an assistant professor at Communication Research Center, International Institute of Information Technology, Hyderabad during 2008-2009. He served as an assistant professor at the Department of Electrical Engineering, IIT Indore, India during 2009-2013. And he worked as an associate professor at the Department of Electrical Engineering, IIT Indore during 2013-2017, where currently he's working as a professor since 2017. He's also an associated faculty with the Department of Biosciences and Biomedical Engineering and Center for Advanced Electronics at IIT Indore. He was a visiting professor at the School of Medicine, Faculty of Health and Medical Sciences, Taylor's University, Malaysia during 2018-2019. He worked as a visitor scholar at Intelligent System Research Center, Ulster University, Northern Ireland, UK during December 2014. He's an associate editor of Electronic Letters, Biomedical Signal Processing and Control Journal, and an editor of IETE Technical Review Journal. He's a senior member of IEEE and fellow of IETE and IET. His research areas are signal processing and image processing, biomedical signal processing, non-stationary signal processing, speech signal processing, brain-computer interfacing, machine learning, and AI in healthcare. He has supervised 12 PhD, 20 MTech, and 41 BTech students for their thesis and projects. He has 255 publications to his credit, which include 136 journal papers, 66 conference papers, 5 books, and 18 book chapters. His publications have around 8,500 citations with a H index of 49. He has been listed in the top H index in the scientists in the area of computer science and electronics by Guide to Research Website Institute. He has been listed in the world's top 2% scientists in the study carried out at Stanford University, USA. He served on the review boards for more than 100 scientific journals and served for scientific committees of various national and international conferences. He's also an honorable member of Indo-South Korea JNC. I cordially invite Professor Pachori for his session. Over to you, sir.
Okay, thank you very much, Vasundhara, for a nice introduction. And I would like to convey my thanks to organizers of First Indo-South Korea Joint Training School on Environmental Cyber Physical Systems for providing me this opportunity. And it is my great pleasure to be part of this school and deliver a talk in this workshop. Thank you very much. Let me share my talk. Yeah, are you able to see the slides?
Yes, sir.
Okay, thank you very much and good morning, everyone. So today's talk is actually focused on fundamentals and applications of signal analysis. So actually, signals we encounter in most of the places, and it is actually very difficult to find any area of research where we don't have signals. And signals actually carry information. And in order to extract information, we need some methods, and that signal processing and signal analysis actually plays important role to extract this information. So commonly used methods actually they are time domain based methods and frequency domain based methods. And so these time domain based methods and frequency domain based methods, they are mostly suitable for stationary signals. And in real life, the most of the signals actually they are non-stationary signals. So for representation and analysis of such kind of signals, there is actually recently this non-stationary signal processing techniques have been developed for analysis of such kind of signals. So in this talk, we will focus on this non-stationary signal analysis technique like short time Fourier transform, wavelet transform. And together with this Fourier transform, motivation, and what is the fundamentals related to signal analysis and various applications of these methods will be provided. So with this background, let us start this talk. So this is the overview of this talk. First, we will see transform, then after that we will see Fourier transform, then short time Fourier transform, then continuous wavelet transform, and after that we will see discrete wavelet transform, and in the end conclusion will be provided. So a transform, that is actually, it is one kind of mapping, and it is mathematical operation which takes you from one domain to other domain. And for example, like Fourier transform, by using this transformation, we can go from time domain to frequency domain. And this is actually, this helps us to perform suitable analysis. Like if you go from time domain to frequency domain, a lot of nice analysis can be done in other domain or frequency domain, and then after doing this analysis or extracting information, we can come back in time domain. So that is actually, it is one kind of bridge between two domains, and by doing this analysis process, we can go from one side to other side, and by doing synthesis process, we can come back from other side to our actual side. So there are various actually reasons and motivations for doing these signal transformations, and we will highlight some of them. So this transform provides certain information about the original function of the signal. So like signals, what are the frequencies present in the signal, which frequency the major frequency, and which frequency the minor frequency, which frequency of the signal is corresponding to signal, which frequency is corresponding to noise. All these informations actually we can obtain with the help of transform. And this transform help us to solve the differential equation. So like in signal systems, like in signal processing, generally we assume that whatever signals we have, that is output of the system. And we actually use mathematical models to represent the system. And when you are doing this analysis of signal, indirectly it is analysis of system. And when you are doing analysis of system, indirectly it is analysis of signal. So signals and systems, they are actually dependent on each other. So when you solve the system, and in order to solve the system, you need to solve differential equation, and transform actually plays important role to solve such kind of mathematical representation of the system in order to understand the signals. So like for example, Laplace transform, Fourier transform, we use to represent actually the system in other domain, to extract the information related to the system and to understand the signal. And other actually this transform, when we perform transformation, then there is actually very important part, the basis functions. And somehow if you are able to select basis functions according to the signal that you are analyzing, in that way the requirement of coefficients will be less. So for example, like selection of spoon depends on the type of food. And if you want to have noodles, then we use fork, because your food is discontinuous and your spoon is also discontinuous. So discontinuous food can be handled nicely with the discontinuous spoon. So similarly, if your signal nature, suppose signal is decaying with time, and somehow you are able to design or select basis functions which are also decaying with time, then requirement of coefficient will be less. And in that way, the signal can be represented with the help of less memory. So requirement of bandwidth will be less. And other advantage that is actually this, like when you implement transform, and by doing this transformation, we go actually one domain to other domain. So like we go from time domain to frequency domain. And when you see in broad manner the signal processing, there are actually three independent forces. One is time, and second one is frequency, and third one is scale. And whatever is happening in this world, it has connection with time. And whatever we listen, it has connection with frequency. And whatever we see, it has connection with the scale. And we will see in this talk the importance of these three independent variables, time, frequency, scale. And by doing this transformation, we go from time domain to frequency domain. So this is actually one of the advantages. Like whatever processing we do, all actually it has dependency on time. But now you are in such a domain, there is no time. So when you are in frequency domain, you are in a scale domain, there is no time information. So your processing, you don't need to depend on time. So for example, like when you implement convolution operation in a linear time invariant system, then we assume that the system is causal. And when you are implementing this convolution in frequency domain, then you don't need to assume any condition about this causality. You don't need to any condition about the time dependency. So this is actually one of the beauty of the transforms. You are going in such a domain where without depending on time, you can do a lot of analysis, and then you can come back in time domain. So we use this convolution theorem. Suppose you want to implement convolution, then you multiply Fourier spectra of these two signals. One is the signals, other one is the impulse response of LTI system, and then again we take inverse transformation and we can come back in time domain. So in that way, we can actually bypass such time domain requirement or time domain dependency on the analysis. So these are actually some of the advantages. That is why we prefer transformations in signal processing and specifically in signal analysis. And you will not find any area of science and technology where transforms are not used. It is actually attached to most of the areas of science and technology. So the simple transform that was proposed by the Fourier actually in 1807, and this Fourier actually, he was from physics background, and when he was performing experiment on the prism, then this white light, it was decomposed into 7 colors, and white light is like complicated, it has a mixture of all colors, and nicely with the help of prism you can decompose into simple components, simple colors, and that is actually, so Fourier got idea, and this Fourier actually thought the similar way that white light can be decomposed into seven colors, we can also decompose this complicated signal in terms of simple signals. So like a complicated signal, whatever we see, like for example, like speech, your biomedical signals, a seismic signal. In nature, we record many signals, vibration signals, man-made signals, natural signals. These all signals actually, they are unknown signals, and we can represent these signals with the help of such kind of representation, like Fourier, where these basis functions, they are known functions. So unknown problem can be represented with the help of known functions, and which actually help us to perform better analysis of the signals. So according to Fourier, this any complicated signal or any unknown signal can be represented with the help of sinusoidal functions, and the sinusoidal functions are very easy to understand, easy to analyze, and that is actually, so the formal definition of this Fourier transform in any function which is continuous or it has finite number of discontinuities can be defined in finite interval with the help of sum of sinusoidal functions. And then actually this was proposed by Fourier in 1807, that all periodic functions can be represented as a sum of trigonometric functions. Then this work was actually submitted for publication, and this Lagrange, Legendre, and Laplace, these are very popular professors of that time, and they were appointed reviewer of his work. And Lagrange actually is well known for Lagrange multiplier. Legendre is well known for Legendre polynomials, and Laplace is well known for Laplace transform. And these actually professors, reviewers, they were having concerns about the Fourier work. And some of the concerns are like that this Fourier actually was representing the signals, real life signals, they are actually real signals. He was representing signal with the help of complex functions. And signals are real, but he was representing using these complex functions. And other problem, most of the signals in real life, they are actually aperiodic signals, and Fourier was using the basis functions which are periodic in nature. And a third concern was this Fourier actually was using such kind of representation where negative frequency and negative time was coming into picture. That it doesn't actually physically, it doesn't make any sense. So due to these problems, these reviewers did not recommend this Fourier's work for publication. But after 15 years, they understood the importance of Fourier's work, and they thought that this what Fourier using this complex representation, which can be considered a general form of the real signals representation, and that way, and that actually in 1822 Fourier's work was finally published. And even today, whatever transform in signal processing we have, we always understand with the help of Fourier transform. So after 1822 up to 143 years, there was no significant work in signal processing. And 1965, this Cooley and Tukey, actually they developed fast Fourier transform. So this Fourier transform actually people wanted to implement with the help of machines, with the help of computers, and then there was a lot of interest to compute such kind of transformations actually with the help of machines. So in 1965, this FFT, that fast Fourier transform, was developed. And now we'll see just a brief overview of the Fourier transform. So according to this Fourier transform, this complicated signal, their complex signals, can be represented with the help of simple signals. So these simple signals are known as basis functions. They are also known as building blocks. They are also known as non-functions, and they are sinusoidal functions. And Fourier transform can be considered as a bridge between time domain and frequency domain. So like if you want to go from time domain to frequency, you can go through analysis process. And if you want to come back from frequency domain to time domain, then you can use synthesis process. So this analysis and synthesis equations for the Fourier transform can be represented mathematically with the help of these equations. So first is analysis equation, where we are integrating signal from minus infinite to plus infinite. So entire time is integrated. So then you are integrated entire time, so there is no time in the frequency domain. And similarly, when you are doing the synthesis process, you are integrating entire frequency from minus infinite to plus infinite. So there is no frequency in the time domain. So when you are in time domain, there is no frequency domain. And when you are in frequency domain, there is no time domain. Time domain and frequency domain, both actually domains are disjoint. They are mutually exclusive. So this is just one example of how this Fourier transform works. So we have taken these three sinusoidal signals in time domain. There are 5 hertz, 25 hertz, and 50 hertz. And when you apply Fourier transform, then you will get the frequency domain. And you can see the first signal has peak at 5 hertz, second one has peak at 25 hertz, and third signal has peak at 50 hertz. So this Fourier transform actually measures the similarity between the basis function and the signal that we want to analyze. So that particular signals what we have considered, they are like similar to basis functions. And if that frequency or that basis function is available in the signal, corresponding to that frequency, there will be peak. Otherwise, it will be zero. So from that, actually, there is a frequency domain representation. We can clearly see that what are the frequencies present in the signal. And now we will see some of the actually shortcomings of the Fourier transform. This Fourier transform tells us what are the frequency components present in the signal, but it does not tell us what time, what frequency is occurring. So like timing information of the frequency components, because we have integrated entire time when we went to this frequency domain. And when you see actually in the signal processing, we do a lot of actually classification of the signals. And one of the classification of the signal is stationary signals and non-stationary signals. We can also classify signals into two classes. One is stationary signals class, and second one is non-stationary signals. And stationary signals, actually we use mathematical models to represent the signal. And if these parameters they are constant with respect to time, then we call them stationary signals. And similarly, any of the parameters of these models are changing with time, then we call them non-stationary signals. And it is very difficult to find any signal in real life stationary signals. Most of the signals we encounter in real life, they are non-stationary signals. So whatever models we use to represent them, their parameters change with time. So for such kind of signals, actually Fourier transform is misleading because it doesn't provide time information, and these signals actually they change with time. Their parameters change with time. So in order to have actually this time varying information together with this time domain information, and together with this frequency domain information, there is actually the motivation of time varying frequency analysis, or time frequency analysis, or time dependent spectral analysis. This is also known as joint time frequency analysis. So we'll see in the coming slides. So this is actually one example. Here you can see the need of time frequency representation. So here we have taken two signals. One is stationary signal and otherwise non-stationary signal. So stationary signal, it has a mixture of three frequency components, and the same frequency components we have considered like earlier, 5 hertz, 25 hertz, 50 hertz, and it is superposition of these three sinusoids. And you can see, so this is at any point of time, these frequency components are there. So this is a stationary signal. And when you apply Fourier transform, it shows the peaks at 3 frequencies, 5 and 25 and 50 hertz. And on the other hand, we have considered actually the concatenation of these 3 sinusoidal functions, and we have designed non-stationary signal. So it has 0 to 0.3 duration. It has 5 hertz sinusoid, and 0.3 to 0.6 second it has 25 hertz sinusoid, and from 0.6 to 1 second it has 50 hertz sinusoid. So this signal actually at different time it has different frequency components, so it is part of non-stationary signals. And when you apply Fourier transform for this kind of signal, then you see that we are getting same spectrum. So this Fourier transform actually is misleading representation. It is misleading because when your signals they are changing with time, in other words, in time domain both signals are different, but in frequency domain you are having actually one kind of only transform. So this one transformation or whatever one this frequency domain can be actually corresponding to 2 time domain. So that is not 1 to 1 mapping. It's not unique representation. It's misleading. And this Fourier transform can be corresponding to stationary signal. It can be corresponding to non-stationary signal. So this also actually one of the strong motivation for time frequency representation, where we can have unique representation of the signal in transform domain. So there is actually these are the 2 motivations that we have seen, and we will see from the basis functions point of view also motivation for time frequency representation. And the sinusoidal functions, they are periodic functions, and they extend from minus infinite to plus infinite, and the resolution, concentration, focus is proportional to 1 upon spread. And the sinusoidal functions, they have infinite spread in time domain. So due to that, there is a nearly 0 resolution in time domain because the spread is infinite. So the sinusoidal functions, they have actually 0 time resolution in ideal case, and they have very good resolution or infinite resolution in frequency domain, because when you apply Fourier transform sinusoidal functions or the spectrum of the sinusoidal function, there is an impulse. The impulse spread is 0, so due to that there is infinite resolution in frequency domain. So this Fourier sinusoidal functions which we use as basis functions in the Fourier transform, they have infinite resolution in frequency domain and 0 resolution in time domain. So due to that, these basis functions, when we use for non-stationary signal analysis, they are not useful. And due to these reasons, there is a need of time dependent frequency representation, and which we also call time frequency representation for non-stationary signals. So the first actually transform that was proposed in the literature for this analysis of non-stationary signals, that is short time Fourier transform, STFT. So what we do actually, we divide this entire signal into different parts, and each part or each segment we assume that signal is stationary, and then we apply Fourier transform to different parts, and then arrangement of these Fourier transform of the different segments gives us short time Fourier transform, STFT. So this is the mathematical representation of short time Fourier transform. Here you can see xt is the signal that we want to analyze, and t is the window function, and t dash is the shifting parameter. So by doing this different values of t dash, we can actually cover signal from beginning to the end. Different parts of the signals can be segmented. And this is a kernel function like a Fourier transform basis function. And here you can see now your basis function, earlier it was function of only frequency, it was frequency shifting, but here now due to this multiplication of this window together with this basis function, now we can consider this basis function is also shifting in time with the t dash parameter. So this this windowed sinusoidal function or windowed this complex exponential function can be considered as a time frequency basis function, because here this basis function now it is covering different time points, at the same time it is covering different frequency points. So this basis function indirectly actually is going in time frequency domain, time frequency representation, time frequency basis function, in contrast to the Fourier, which was only in frequency domain, which was covering only frequency axis. So here you are covering actually both axis, time and frequency. So due to that, these basis functions we call time frequency basis functions. And when you perform this integration, and then actually in the left hand side you see there are 2 independent parameters, time parameter and frequency parameter, T dash and omega. So T dash actually includes time information and omega includes frequency information. So this short time Fourier transform, whatever we compute, which is function of time and frequency. So that actually gives you time frequency representation, and together with frequency domain, here also we have time domain. So actually in some books they call it time frequency bedding, like time and frequency domain both are married and now they will stay together, and together they can actually fight with the non-Stacy signals in better way. So this is one example. Here you can see this is the signal, non-state signal. In the beginning of this we have high frequency component, then we have low frequency component, then we have high frequency component, and we have this window, and then we have T dash equal to -8, then T dash equal to -2. Different time we can actually shift it. So different parts of the signal can be analyzed with this window function, and this window is uniform for each part of the signal. So this HTFT actually is a complex quantity. For the representation purpose, we take square of the magnitude of the HTFT, that is known as spectrogram. And spectrogram is actually non-linear operator, whereas this HTFT is a linear operator. And this Geber 1946 actually suggested use of Gaussian window for computing short time Fourier transform. So when you compute HTFT with the Gaussian window, then it is known as Geber transform. And this is actually till today this Gaussian window is or the optimum window. Like if you take Fourier transform of the Gaussian window, that is again Gaussian in frequency domain. So that is actually, this is the only function which has similar nature in both domain. So that is actually a beauty of this kind of functions, and that is why they are optimum functions. And this Geber transform is the optimum short time Fourier transform, and that is actually proposed by the Geber. And this is one example where you can see this spectrogram and for speech signal. And this study has been carried out in MATLAB. And when you speak MATLAB, so when you speak MATLAB, then this is a speech signal in time domain, and we can apply spectrogram. And based on the size of the window, we call it narrowband spectrogram and wideband spectrogram. So narrowband spectrogram is in time domain we have large window, and wideband spectrogram in time domain we have short window. So here this example 256 samples window we have considered in time domain, and for wideband spectrogram we have considered 64 samples short window in time domain. So here you can see this actually narrowband spectrogram that I mentioned you, the resolution, focus, concentration, the proportional to 1 upon spread. And here since the spread is narrow in frequency domain, so it has good resolution. So this narrowband spectrogram has very good resolution in frequency domain. On the other hand, when you go wideband spectrogram, there is actually blurring kind of phenomena in the different frequency components present in the speech signal, or the formats they are present in the speech signal. That is blurring, and that is the thing. Actually, frequency components are not clear. They are merging to each other. But on the other hand, you can see well separated frequency components in the narrowband spectrogram. So according to actually your requirement, you can use different kind of windows in order to have different kind of spectrogram. So in MATLAB, actually there is a spectrogram command is there, and you can use this command, and nicely you can compute this spectrogram. And there are various inputs. You can give your signal, number of 50 points, sampling rate, which window you want to have, and what is the overlapping. And this is another signal, chirp signal, and it's actually this in time domain, its frequency changing linearly with time. And that you can see from the narrowband spectrogram with good frequency resolution, and with the wideband spectrogram with the poor frequency resolution. And when you apply Fourier transform, there is no time information in the spectrum, but here you can see this frequency changing linearly with time. So this time frequency representation gives you the proper actually representation or proper information about the signal that is actually evidence from this time frequency time frequency plane. So in actually MATLAB there is chirp command which generates chirp signals, and then spectrogram is already there which can compute a spectrogram of that signal. This shortcomings of the HTFT, this actually short time Fourier transform, what we do, we are dividing into signal different time segments, and with the help of sliding window function. And there is no thumb rule how to select size of the window and type of the window. It is a very serious problem. And if you have low frequency component, then you want to have wide analysis window. If you have high frequency component, then you want to have narrow analysis window. And high frequency components you want to have good time resolution, and low frequency component you want to have good frequency resolution or poor time resolution. That is, that facility is not available in short time Fourier transform. For that we need adaptive window, because this STFT window size is fixed and type of the window is also fixed. So there are various windows in the literature: Bartlett window, Blackman window, Baumann window, Chebyshev window, Hamming window, Henning, Kaiser, rectangular window, triangular window, Gaussian window. And according to a requirement, actually, one can use this window function for the analysis, but for the study purpose. And there actually this window sizes or this resolution, they are connected with the Heisenberg uncertainty principle. So this delta t, that is actually spread of the signal in time domain. Delta f, this is the spread of the signal in frequency domain. That is, they are connected with this uncertainty principle, greater than equals to 1/4 pi. So this equal point, that is for Gaussian function, and this inequality, that is for other functions. Equality for Gaussian functions. And here the delta t is spread of the signal in time domain, that is also known as duration, and the spread of the signal in frequency domain, that is also known as bandwidth. So according to this principle, if you increase the duration of the signal, then spread will be reduced. On the other hand, if you increase the bandwidth of the signal, or increase the duration of the signal, then bandwidth will be reduced, and it is vice versa. And if you reduce the duration of the signal, then bandwidth will increase. So at the same time, you cannot have actually good resolution in broad domain. So like if you reduce bandwidth, then you have good time resolution, good frequency resolution, and if you reduce duration of the signal, then you have good time resolution. But when you are reducing this duration of the signal, at the same time this bandwidth will increase. So resolution in other domain will be poor. So according to this Heisenberg uncertainty principle, at the same time we cannot have time and frequency resolution very high. That is actually, this is not in our hand, or this is not due to signal processing algorithm. This is due to the principle which is imposed by the nature. That is we call Heisenberg uncertainty principle. And how to solve this problem, that actually we have seen in STFT, this fixed window problem, that is actually solved done by the scale concept. So by using scale, we can have different kind of actually basis function, adaptive window we can design. So when you use low scale, then your window will be like suitable for the high frequency component, and when you have large scale, then it is suitable for low frequency component. So with different scales, we can actually design wavelets, and that is actually suitable for the analysis. So that is actually the idea of the wavelet. So wavelet is a symmetric waveform of limited duration which has an average value of 0. And here you can see some foods are better handled with a fork than a spoon, and you can see here. So like for different kind of foods, you can design actually different kind of spoons here. So similarly, like different frequency component present to the signal, and we can have now different kind of scales that is suitable for different frequency component which are present in the signal. That is actually the concept of wavelet. So we are analyzing signal with the help of all possible scales, and we believe that at least one scale will match with the requirement of the analysis. And this actually, it helps us to solve the resolution problem of the STFT, where we use this here variable length window with the help of scale. And narrow window analysis can be done for high frequency component with the help of low scale. And similarly, wide window analysis can be done for the low frequency component based on the large scale. So low scale gives you good time resolution, and large scale gives you poor time resolution. So this actually wavelet transform works well if the signal that we want to analyze, it has low and high frequency both components together. So we can use different scales to analyze different kind of frequency component present in the signal with different resolution, that we call multi-resolution analysis. And that is actually that is very useful. If only signal has your low frequency component or high frequency component, then STFT is better. You don't need to use this wavelet transform. So this is actually mathematical representation of continuous wavelet transform, and here you can see actually the signal that we want to analyze, and the site is the mother wavelet, and by using this parameter tau and s, this shifting parameter or transition parameter and scale parameter, we can design these daughter wavelets. And nicely this 1 upon under root s, this normalization constant actually ensures that whatever daughter wavelets you are designing, they have similar energy like mother wavelet. So this even each daughter wavelet also can be used as a mother wavelet. So in that way, this actually the signal actually is analyzed with the all possible scales. So it is like big library of the basis functions, and we believe that at least one scale will match with the requirement. And when you analyze it, then you have actually in transform domain, left hand side, this continuous wavelet transform is a function of two independent variables tau and s. So this time parameter and scale is scale parameter, and the scale can be converted into frequency with the help of this relation. Scale is proportional to 1 upon frequency, so that this time scale representation which we get from the wavelet transform, we call it, we can also obtain time frequency representation. So this is actually very nice example which will explain you use of scale. So now same example that we consider in STFT. Here we have then a high frequency. In the beginning, this signal is high frequency component, then low frequency component, then high frequency component, and s equal to 0.1. So this is like a low scale, so which is suitable for high frequency component. And once you design this window at low scale, then you will move it around around the signal. So like that you can cover different, you can use this scale window like STFT. And again we will increase the scale. So now it is suitable for low frequency component. Then again we will move this around the signal like STFT. So that is actually a sliding window, but we use different scales. Again we have increased the scale, and again we have increased the scale. So you can see now what we are doing, we are analyzing signal with the very low scale, medium scale, large scale, all possible scales. So like here in this case, this maybe this scale is suitable for the middle part of the signal, and the very low scale, and here you can see this may be suitable for the initial part of high frequency component of the signal. So in that way we are actually using different scales for different frequency components present in the signal. And this is actually history of this time frequency representation, the multi-resolution property. So Shannon actually 1949, he represented signal with the help of impulse functions, and these impulses are actually like basis functions, and impulses, they are well localized in time, and the speed of the impulse in time domain is 0. So due to that it has infinite resolution in time domain, but with 0 resolution in frequency domain. Fourier represented signal in terms of sinusoidal functions which are actually impulse in frequency domain. So this actually in France, people call this Fourier as a Newton of the France, because without knowing sampling in time domain, he sampled signal in frequency domain. So like Shannon represented signal in terms of impulses in time domain, Fourier also represented impulse signal in terms of impulses in frequency domain, and but without knowing the sampling in time domain. So that is actually one kind of very surprise. That is, people call him Newton of the France, because he represented a signal in terms of impulses in frequency domain, and without knowing time domain representation in terms of impulses, that proposed by the Shannon in 1949. And so this upward frequency domain proposed by the Fourier, which has actually impulses in frequency domain, so it has infinite resolution in frequency domain, and these impulses have very low resolution or 0 resolution in time domain. Then Geber represented signal in terms of basis function time frequency domain, which are well localized in time frequency domain, but their area is fixed. And that's, so this is like fixed resolution basis functions, and each basis function has fixed resolution in time frequency domain. And this wavelet that actually it has multi-resolution analysis, like at any point of time we are representing signal with all possible scales. So here you can see it has actually scale is less, low scale, so it has good time resolution. Here scale is a little bit large, so it has poor time resolution, and here scale is very high, so it is actually poorest time resolution. So in that every point of time you have all possible resolutions, all possible scales. That is actually that is multi-resolution analysis. So you are using different all possible scales at a given point of time, and in that way you can analyze signal with all possible scales. And this is a history. In 1970, the Smollett, he was geophysical engineer. Actually, he come up with this idea of windows that is generated by the dilation and compression of the prototype small oscillating signal that is called wavelet. And it got a lot of criticism because there's lack of mathematical proof. It was just empirical idea. The 1980s, Grossman, he was theoretical physicist, and he formalized the transform and devised the inverse transformation that is called first wavelet transform. And 1984-1985, Bayer developed orthogonal wavelet basis functions with better time and frequency localization. And Dubéchi actually, she has done a lot of work in this wavelet, and she's one of the pioneer. And based on her name, there are DB1, DB2, DB3, DB4 wavelets. And she also proposed discretization of time and scale parameters of the wavelet transform, wavelet frames concept. She also proposed orthonormal basis of compactly supported wavelets in 1988. And then Stephen Mallat, actually he's from France. He is the first person who proposed this multi-resolution analysis. That was part of his PhD thesis in 1988. And whatever today discrete wavelet transform we use, that is also proposed by the Mallat, that we call Mallat algorithm, that we will also see in this talk. And cascade algorithm for computing discrete wavelet transform. So the DWT is very easy to compute with the help of cascade algorithm that was proposed by the Mallat. And Martin Bitterli and Jelena Kovacevic, and actually both actually they are from EPFL, this group. So Jelena, they are very strong group in the wavelet based research. And they have done a lot of work actually. This wavelets and filter bank they proposed the perfect reconstruction of the signals with the help of finite impulse response filter banks, subband coding, multi-dimensional filter bank. They also extended this wavelet concept for videos, images, and the analysis and synthesis. A lot of contribution was made by the Bitterli and his team. And this is similar to like a spectrogram. Here in wavelet, we call it scaleogram. And this is like in the representation, for the representation purpose, we take square of the square magnitude of the wavelet transform that we call scaleogram. And this is nonlinear operator, and it also has cost terms when frequencies are very close. So in MATLAB, there is a CWT command which can be used to compute the scaleogram, and you just give the signal and range of the frequency scales and the wavelet name and plot. If you provide these inputs, then it will give you nice scaleogram in the MATLAB. And we'll see one example, like this is the signal in time domain, and this is finite signal, finite duration signal, and which has infinite bandwidth, all frequency component present in the signal. And when you apply this continuous wavelet transform based scaleogram, there you can see this time, x-axis and y-axis scale. And at low scale, you have good time resolution, and large scale, you have poor time resolution. So because spread is less in time domain, so that's why we are calling it good resolution in time domain. And the spread in time domain is actually very high, so this is poor time resolution. So that is actually, we can have analysis of all frequency components. Scale is proportional to frequency, 1 upon frequency, and with the different kind of resolution. So that is actually the beauty of the wavelet transform. And this is also can be done with the help of MATLAB. So I will share these slides with all of you. You can go through it, and the CWT command you use, and you can perfectly get a scaleogram. And this is another signal in time domain, which frequency is decreasing with time, 30 Hz, 20 Hz, 10 Hz, and 5 Hz. And when you apply scaleogram, nicely you can see this scale is changing with time. So, and each actually component has different kind of resolution, different kind of spread. So you have actually multi-resolution analysis, and that is actually requirement of the analysis. So now this continuous wavelet transform, actually it is very difficult to implement on the computers because computers have infinite memory. So these continuous variables like shifting parameter, scale parameter, you need to discretize them. So when you discretize them, then this continuous wavelet transform is known as discrete wavelet transform, and this daughter wavelet that is actually discretized form of the total wavelet. And this is when you use discrete wavelet transform, discrete wavelet in this continuous wavelet transform, then this resulting wavelet transform known as discrete wavelet transform DWT, and which can be implemented with the help of this filter bank. So you have signal, and then you have high pass through high pass filter, low pass filter, and downsample by 2. So which gives you approximation detail. So low frequency component that we call approximation, and high frequency component that we call detail. And this Malat actually, he did not decompose this detail component, because most of the real life signals, they have low frequency components in significant manner. There is a insignificant high frequency component. So he presented only again decomposed low frequency component approximation part into detail and approximation. So in that way, we can have actually analysis part, and from that, according to your requirement, we can select the number of subbands which you want to include in the reconstruction, and then we perform the synthesis operation, and based on that we can recurse the signal. So this is actually very useful for compression. And this high frequency components, we cannot see, high frequency components we cannot listen, so better to throw them. So this is the basic actually idea of the compression that we consider in the signal analysis, signal processing. So this DWT implementation also can be shown in this way. So you have signal, then you apply a high pass filter, low pass filter, downsample by 2, downsample. So this will give you the approximation first level, detail at first level. Then approximation first level will be decomposed into 2 parts, approximation second level, detail and third level, second level. Then approximation second level can be decomposed into 2 parts, approximation third level, and detail at third level. So in one way actually this can be represented as a spectrum like Fourier transform. So if you combine A3, D3, D2, D1, then your spectrum will be having length like signal length. So there is one-to-one mapping. So sometimes actually in literature, people use this as a A3, D3, D2, D1, these set of coefficients as a spectrum, and as an alternate of the Fourier transform. And how to implement this DWT in MATLAB? So there is actually DWT command for the signal. You just take signal and give the wavelet name, and it will give you 2 components, approximate detail. And if you want to again decompose this approximation, then instead of signal you can take approximation, again it will give you 2 components. So in that way, this decomposition can be done at various levels. So these are commonly used wavelets, Duvachy's at low scale, and this is at large scale. Similarly, this Haar wavelet, this is at low scale, it is a large scale. And it depends on the nature of the signal. If signal is continuous, then we can go for Duvachy's wavelet. And if your signal is discontinuous, then we can go for Haar wavelet. And this now we will see some examples. So DWT decomposition, approximation detail. So this signal is actually noisy, and it can be decomposed into approximation detail by using this DWT. And this approximation part, which actually covers signal part, and the other detail part covers noise. So again, we can decompose this approximation into 2 parts like approximate detail. So in that way, actually all details will be corresponding to noise, and in that way, in the signal actually noise part can be filtered out. And only when you go for low frequency side and higher level of decomposition, your signal part will become more pure, more noise free, more enhanced signal. So that is actually concept of denoising that we will see. So this is actually in MATLAB, there is wave menu command that also can be used to implement this wave DWT. So here you can load your signal. So this is a signal, and then you can perform. So in this example, we have performed this 5 level decomposition. So we have approximation at 5th level, detail and 5th level, detail and 4th level, detail and 3rd level, detail and 2nd level, detail and 1st level. And then actually there are various applications of wavelets like compression, denoising, feature extraction, discontinuity detection, data analysis with biological data and financial data. So this you can see this is the actually signal, and which can be represented with the help of very less number of coefficients in DWT. So which actually gives you the compression in other domains. So in wavelet domain, you go and you just represent signal in terms of DWT coefficients, and you can have very less coefficients. So you can have more actually use of you can have more memory to store other kind of signals, and that is actually different kind of compressions actually can be obtained. And you can see the signal is compressed with the factor of 16, and out of 16 coefficient we have only taken 1 coefficient, others we have made 0, And then also you can see the reconstructed signal using this DWT is like actual signal. And this is actually, we have shown this for electrocardiogram ECG signal, and that you can see the signal can be compressed with different factors. So, and when you use the compression factor 16, then also this PQRS pattern that is actually preserved in the ECG signal. And the denoising also can be done. So this signal is actually noisy, and you can have different actually bands, approximate fifth level, detailed fifth level, detailed fourth level, third level, second, first level. And you can see these details, they are like noise, and you can remove them and you can reconstruct signal from the approximation parts. Discontinuity can be detected using DWT. So the signal doesn't actually, you cannot see any discontinuity. But if you decompose this using wavelet DWT first level, then this is approximation part and this is D1 is detail part. And detail part you can see nicely discontinuity present in the signal. This is very useful in power quality analysis. And discontinuity detection also can be done using CWT, scaleogram, and you can use some particular scale from this scaleogram to see it more clearly. So this is actually conclusion of this talk. Time frequency representation is a general representation of frequency representation, similar to non-stacy signal is a general representation of stacy signal. And problems in time frequency representation like short time Fourier transform, the selection of type and size of window function, there is no thumb rule for that. And wavelet transform, selection of mother wavelet and number of labels, that is not actually ruled. According to this like trial and error, we do such kind of analysis. And time frequency analysis is an active area of research. So this is just actually, I have presented the basics of the signal analysis, time frequency representation. But recently there are various advanced signal processing techniques like variational mode decomposition, empirical mode decomposition, Fourier Bessel series expansion based empirical wavelet transform, Synchro squeezed wavelet transform, tunable Q wavelet transform, empirical wavelet transform, flexible analytic wavelet transform. There are various actually techniques recently have been proposed. So you go through them, and I hope with this background you will be nicely you can understand them, these techniques. So these are the actually references that this talk is based on these references. So in order to understand it more and more detailed information, I request all of you to go through these references. And thank you very much for your time for time frequency analysis.
Yeah, Basundhara, you are on mute.
Sorry. So thank you very much, sir. We'll open the floor for questions. We have one question in the chat box as of now. This is from Mr. Lakshmikant. He's asking, can resolution improve with compressive sensing?
Yeah, that is actually this compression sensing, that is also this way of actually compression. So resolution is actually, it depends on the your basic components. And if you are using compression sensing as a basic representation, then you can change, you can improve it. If you are using just a processing part, then it doesn't have any connection with the resolution. So if you are able to use this compression sensing as a basic representation of the signal, then yes. Otherwise, it is just processing. You are doing just compression by doing this, and then it's.
Okay, sir. Thank you. The attendees may unmute themselves if they want to ask any questions. Sir, I don't think we have any questions as of now.
Okay. So,
but obviously,
yeah.
Yes, sir, please go ahead.
Yeah, what I will do, I will actually share this talk with you, and I request all participants, if you have any questions, please feel free to write me, and it is my pleasure to answer these queries.
So, thanks a lot, sir. You may stop sharing your screen. And this was a very informative session. You have covered so many concepts related to signal analysis along with MATLAB simulations, which made it even more interesting. So it was really an insightful talk, and it was a pleasure to hear you. Thank you very much, sir.
Thank you very much. Thank you for this opportunity.